Hello friends, welcome to MATLAB school. In this video, we are going to simulate sensorless control of BLDC motor using initial stator voltage injection method. So in this method, we are going to use a system which doesn't have a speed encoder. Instead of having a speed encoder, we will be using the Hall sensor. Uh, Obviously, as you know, since this being a BLDC motor, there's a requirement of Hall sensor to be placed at the rotor. So, so to detect the position of the rotor, we need to have Hall sensor. So by using a bus selector, you you can you can open the or you can select the things that you want to have. So here, since we need the Hall sensor signals, I have selected the Hall sensor A, B, and C. So this Hall sensors data will be given to the next stage. So here in the decoder, we are doing the estimation of direction of back EMF. So based on the value that we get from the Hall sensor, we'll be determining the uh, the position or the region of the back EMF. So -1 corresponds to the negative direction of back EMF, +1 corresponds to the positive direction of back EMF, and 0 corresponds to the nil value of back EMF. So the peculiar thing about this model is initially for a time duration of uh, zero point zero 0.02 seconds, we'll be injecting some pulses, so which will make the motor to start. Okay, so only if you know, if you rotate the motor initially, the Hall sensor will start detecting the position of the rotor. Later we can switch on the corresponding stator winding, which will make the rotor to rotate continuously. So to get this data, we have a file already placed there in the workspace. So if you want to have this data, just click workspace data. See, you will be getting the data that you need uh, to be, I mean, to be signaled to this decoder block. Okay, so since we are using this data, see, this data will be in the form of uh, time series signal in most of the cases. So this data will be fed to this decoder block up to a time duration of 0.02 seconds. So this will inject a pulse. So that pulse injection will make the rotor to rotate initially, and once the rotor starts to rotate initially, then the Hall sensor will start detecting the position of the rotor. Then later on, the speed of the motor will be controlled. So here we have used a peculiar technique to control the speed. See, these data are coming from the Hall sensors. So initially the Hall sensor data will be in the form of pulses. Later it will be, it will be in the shape of square wave. Um, then it will be converted to pulses by using these three edge detectors. So it will be detecting the rising edge, and we are muxing it. We are putting it to go through the AND gate, OR gate. So we'll be getting three continuous pulses. Okay, so we shall see it with the help of waveform once we simulate the model. So then it will be incremented by using up counter. Then later on it will be differentiated to find out the speed from the position of Hall sensor. So we are differentiating it here. Okay, and later on we are finding the value of speed just by dividing uh, the speed variation or the angle variation. We can uh, consider this as d a, divided by dt. So this will be finding out the value of speed. So here also we have the provision to give the feedback. So actually the feedback is coming from the Hall sensor. Uh, so since we are trying to estimate the rotor position, also the speed of the motor uh, by means of sensing the rotor position by the Hall sensor data. Uh, see the after speed calculation. See, this is not EMF actually. This is uh, the speed. So this speed will be compared with the actual speed. I mean reference speed. Here we have given a reference of 1000 RPM, and once this once the time reaches 0.75 seconds, the speed will be changed to 1500. So that would be our reference speed. Our actual speed will be compared with this reference speed. We shall see the speed getting settled at 1000 RPM until 0.75 seconds, and later on the speed will change to 1500 RPM. So here we have a PA controller that will control the speed by reducing the error between the reference speed and the actual speed. So let us simulate the model. Let us open the speed scope. Yes, the model has started to run. So let us open the speed scope. Yes. So this is the initial voltage uh, injection. So after that injection, after point not 2 seconds, the speed will be estimated from the Hall sensors data. So as you know, the speed will get changed when the time reaches 0.75. So now it is 0.5. At this point, it will get changed. Yes. So it is getting settled at 1500 RPM. Yes. So it is settling perfectly at 1500 RPM. So we can see the current waveforms. Yes, these are the current waveforms. We shall see the full waveform now. Yes, the simulation has completed. Okay, let us wait for the waveform to get aligned properly. Yes, it is come, I think. So this point corresponds to the changeover of speed. So at this point, you could see the speed getting changed from 1000 RPM to 1500 RPM. Uh, then we have torque. Let us see the torque waveform. Yes, this is the torque waveform. So as you can see, there is a change in torque or a spike in torque during the time of speed change. The So for a time duration of 0.02 seconds, we'll be uh, giving a pulse width of zero point 0.8. In the sense, the duty cycle will be kept at 80 percentage until the time reaches 0.02 second. And after that, the pulse width will be coming from the closed loop controller controlled by PI controller. So here we have the 6 switches which are responsible for controlling the speed of the motor. So as you can see here, you can uh, see two things. One is the control logic for controlling the speed, and the other logic uh, which are coming from these two blocks. So these two blocks are responsible for deciding on which switch to excite at that particular time. In the sense, we'll be trying to excite the uh, stator winding which is very nearer to the uh, uh, rotor at that point in time. So that's the logic behind this. So then we shall open this scope. So this scope will be displaying the SOCF battery, the current uh, drawn and supplied by the battery. Then this is the voltage across the terminals of the battery. Yes. So these are the signals which are coming from the uh, uh, I mean the Hall sensor. So these square pulses, square waves, if you zoom this, it will be a square wave. See, it will be a square wave. So these square waves will be converted to train of pulses. Okay. So these square waves will be converted to train of pulses at this point, and later it will be counted. The number of pulses will be counted. Okay. So after counting, we are finding out the value of I mean the slope, and it will be multiplied by the constant, which will give you the speed. Uh, Hope this video is useful to you. The same video is available for download in the link given in the description. If you want, you can download it and you can use it for your purpose. Thanks for watching. Well, please do like and subscribe our channel. Also, please share our channel among your friends. Thanks for watching.